So framing word embedding as metric recovery of a semantic space unifies existing word embedding algorithm and so ties them to manifold learning. So existing algorithms are metric recovery methods, for example, co-occurrence counts from random walks. And for example, in inductive reasoning in semantic space, you say that we have A, we have B, we have C, we have D, and some other things like D1, D2, D4. But I, here I, A, B, C are given, and I is the ideal point, and D are choices. So the correct answer is just the shaded region. So what I want to say is that, like metric learning, that another good example is that, for example, here you have some word like ideology, art, science, and research. And you have other words like corruption in Iran. And in metric learning, so these words these words that are in blue are clustered together. The distances is reduced because they're talking about wisdom. But here, although, for example, here we have so before metric learning is like that. You have some words like corruption, ideology. So I think this one should be red. Art, science, computer science, research, those things are blue, and so in after metric learning you can just make two clusters. These two things are near each other, so they represent the ignorance. And the distance between x and y is just x minus y transpose. You want to learn your S, your metric, and you understand what is the natural metric, because if you just use the Euclidean metric, you cannot say that ideology is the same as those people talk about science, because it's a different world. And that's why you should capture metric learning. Of course, I have a playlist about metric embedding, more than 20 lectures, but all of them are just classical metric embedding thing. In metric learning, it's a little bit different thing, because you want to learn the original metric, because you don't want to just cut off by thresholding the Euclidean or any other metric that you have and use the shortest path, but because your problem is more is you're looking at the problem as a different perspective. You just want to calculate it because your deep mind, deep learning paradigm pushes you to do calculations rather than observation. So that's why people in metric learning are solving another problem, which is different from metric embedding. Of course, they could have some intersections, some ideas that are similar to each other, but in general, they're talking about two different things, two different goals. And not two different goals, but two different approaches, let's say. And in all these things, you always use the distributional hypothesis. I mean, Harris 1954, that similar concepts imply similar meanings. And the Euclidean vector space is not a valid representation of semantic concepts. So we must relate co-occurrence to semantic similarity assessments. A good test of statistics for geometric sampling to see if words are consistent with a Euclidean space representation is the concept of centrality. For example, C is 1 over n. Nij, where Nij is just 1 if and if I and j are the nearest neighbor. The interesting thing is the limit. When n goes to infinity, you get c less than equal to 2 with high probability. And now I want to talk about the random walk model that I briefly mentioned. So it's just a simple random walk over words with the following transition probability from word I to j. For example, h is unknown but sub-Gaussian function. And you know, sub-Gaussian, it means it has strong, when I say sub-Gaussian, it means it has strong tail decays. It means that probability of x greater than t, this is the tail, this rarely happens, so it's less than, so it's exponentially decaying, so it's never used or is used very rarely. And now manifold learning, in machine learning we have manifold learning, is finding an embedding of v1 vn into rd that preserve the structure of your manifold by approximately preserving the distances between the points in this manifold. So we can think about all of those things, word embedding, GloVe, and those things as just metric recovery. For example, in GloVe, we just minimize the f of Cij, and this is usually the minimum of Cij and 100 times 2 times xi hat and ci hat plus your bias, another bias, and minus log of Cij, co-occurrence matrix. And so you can represent it as, because if you just substitute ai to be ai hat minus xi hat squared and bj the same thing, you will realize that the thing that is appearing is just the norm cj hat. And this is the weighted and multidimensional scaling. But in Word2Vec, what you want to minimize is just ij, cij, log of exponential of that norm that I said, xi hat minus cj hat squared plus bj hat. So this article is reminding us that all of these things are just metric recovery. For example, in Word2Vec it has a different form, in GloVe it has this form. So the function, so it's a function of the norm, and that matters, that people, so different metric representation could lead to different results. That's why the result of GloVe is different from from word to vec or any other algorithm. So now I want to talk about another article, which is written by Geoffrey Hinton. I like Geoffrey Hinton because of his example about supermarket when he's teaching semantic hashing. So the title of the article is Semantic Hashing in 2009 by Ruslan Salakutnikov and Geoffrey Hinton. Now documents are mapped to memory addresses in such a way that semantically similar documents are located at nearby addresses. So documents similar to query document can then be found by just simply accessing all the addresses that differ by only a few bits from the address of the query document. But what is the pros of that? It's much faster than locality-sensitive hashing. Of course, one thing about locality-sensitive hashing that machine learning guys do not like because it's originally arises from the need for the desire in information retrieval, but in machine learning, of course, even in information retrieval, LSH is because LSH is data independent. It doesn't care about distances between the words, so it does not represent semantic stuff. And that's why we need other kinds of hashing that preserve distances when after hashing or after any kind of embeddings. It's just like metric embedding that you want to reduce your distraction as much as possible. Distortion as much as possible. So we have a latent semantic analysis, which is a linear method, but it can, LSA, it can only capture pointwise correlation between words. And we use SVD to extract low-dimensional semantic structure and then apply it to word document co-occurrence matrix. But linear LEA is inaccurate approximation to variational inference because exact inference is intractable. One thing about information retrieval is that we want to find documents of an unstructured nature, for example, text, that satisfies an information need from within the large collection. I recommend you to watch all of the lectures of Christopher Manning. I really like his lectures, and and you know that Christopher Manning is just inventor of Glovey. You should know that. So you have a user query, and then it goes to query processing. I want to summarize his lectures very quickly. And then we have indexer. Of course, he's not teaching like this, but I just want to say that information retrieval is can be used for many things like collaborating, filtering, like semantic hashing, understanding many different things. And after indexing, you want to score and rank, and then your resulting page that Google shows you. So these algorithms are used in Google very much. So you have document collection, and you give it to information retrieval system, and it gives you a set of relevant documents. Of course, your query goes to the information retrieval system. But what is important for your hashing, such as LSH, is that it should preserve your ranking. And what is ranking? First, you need to know what is recall and what is precision. Recall is the number of retrieved relevant documents to the total relevant documents, but precision, so these are good measures to understand if your information retrieval algorithm works good or not, or what is the problems in what data it has, in what corpora it has some problems, and what are the pros and cons of your algorithm. So the number of relevant retrieval documents divided by the number of retrieved documents is precision. So when I say, for example, ranking for first one is, for example, the recall has become 0.17, 0.4187, because, for example, these are relevant documents, these are irrelevant documents. This is relevant, and this is not relevant. And so this is the recall of that, and then the precision. Precision, for example, 1.2, 0.3, 0.8, 0.7.2. So using these two measures, recall and precision in information retrieval, you can understand if your information retrieval system is working good or not. Is working pretty accurate or not. So I just wanted to recall some ideas about information retrieval, but our goal is quite similar, because now we have a new retrieval method. It's called semantic hashing. So it produces a list of similar documents that is independent of the size of document collection. This method must store 1 word of memory per document, and the lowest layer word document vector of a document. So for example, in constraint, as you look at the original paper, in constraint Poisson model, we have P of Vi equal to N. Given your hidden, this is your hidden topic features, and this is your word count. So the constraint Poisson model is the Poisson of N and e to the lambda I plus Hj Wj times N, of course, and the summation over the same thing, Hj Wkj. First of all, the Poisson of N and lambda, I should recall that this is just e to the minus lambda to the N divided by N factorial. And capital N is just the total length of documents. So N is just the summation over all of your VI. So the probability that your hidden topic is 1 given V is sigmoid of Bj, this is bias of feature J, plus Wij, this is the symmetric interaction between word I and feature J. times vi. So this is just 1 over 1 plus e to the minus x. So the idea is that, and